I want to continue on with our Unit 2, Atomic Theory and Nuclear Reactions, or ATOMS unit. And you can use this to fill in your notes if you weren't in class or if your class hasn't met yet, okay? So we will pick up with isotopes. And a big thing to make a note of right here is the definition of an isotope. So an isotope is going to be an atom of the same element, and the only thing that will be different about it is that it has a different number of neutrons. Now this same element part is important because if you remember, what part of the atom determines the atom's identity? And so you should be telling yourself, oh, hey, Mrs. Miller, that is its number of protons. If we change the number of protons of an atom, we're going to change the identity of the element. And I'll keep saying that because it's super important. And so let's think about our isotope here. The number of protons is not going to change, but the number of neutrons will change. And because of that, the mass is going to change because these are our two atomic particles that have mass. Protons have mass and neutrons have mass. And so the mass number is going to be the number of protons and the number of neutrons. It is not found on the periodic table because if we add the number of protons and the number of neutrons, you will get a whole number. If you look at the periodic table, most of the masses of the elements listed on the periodic table are not whole numbers. And that is because the mass number does not consider the electrons, only the parts that contribute to the mass, but the mass number is the number of protons and neutrons. We're going to talk about how we get the mass on the periodic table a little bit later in this lecture. So symbol for isotopes, it's going to contain the element symbol, the atomic number, and the mass number. So carbon, let's take a look, for instance, at the 3 isotopes of carbon. And so the symbol for isotope will have the element symbol, the atomic number, and the atomic number will be in the lower left-hand corner. And my atomic number is not going to change because this is carbon. Atomic number is your number of protons, and the number of protons determines the identity of the atom. So our atomic number is on the bottom, and then our mass number is on the top. And so our carbon 12 has 6 protons. And how many neutrons will it have? Well, the total mass is 12. We already have 6. So 12 minus 6 is 6. So there are 6 neutrons. Carbon 13, it's still carbon, so there's 6 protons, but now we have 7 neutrons. Carbon 14, it's still carbon, so it's still going to have 6 protons, but now it's going to have 8 neutrons. So naming the isotope, carbon, we'll use the written out name of the element, and then we'll use the mass number, a dash, and then the mass number. So we have carbon 12, we have carbon 13, and we have carbon 14. And I can't stress again that the atomic number of all 3 of these will be the same because atomic number determines element identity, and since they're all carbon, they will all have 6 protons. So the mass of atoms is going to be measured, in AMUs, which are atomic mass units. And the definition of an atomic mass unit is 1/12 the mass of a carbon 12 atom. The atomic mass And I want to go back and just show you the difference. We have atomic mass here. Let me go back. This is a mass number. So we have a mass number and we have atomic mass. They are not the same thing. So the atomic mass is going to be, the weighted average mass of all of the isotopes of a specific element. It is usually not a whole number. This is the one that appears on the periodic table. And so to calculate the average atomic mass, each isotope is going to have a different mass number. We saw that with the carbons. We had carbon 12, we had carbon 13, and we had carbon 14, okay? So each isotope is going to have a different mass number. In nature, most elements are a mixture of isotopes. So the carbon that we find out in the environment is a mixture of carbon 12 and carbon 13 and carbon 14. So in nature, most elements are a mixture of isotopes, and the relative abundance of those isotopes is constant. So to determine the average atomic mass for an element, the formula is this little sigma thing, which is the sum of the percent natural abundance as a decimal times the mass of the isotope. And so to do these kind of problems, we'll work this one together. I'll do it over on the side here. It says that magnesium has 3 isotopes, 78.99% magnesium 24, and magnesium 24, they're pretty specific, has this mass, 23.9850. 10% is magnesium 25, and it has a mass of this. And the rest, well, what's the rest? Okay, if you grab your calculator, and I'll get mine, let's figure out what the rest is. Okay, well, we have to end up with 100% minus the 78.99% minus the 10%. So we have 11% left, if I did that right, 11.01%. So that means 11.01% is magnesium 26. So if we follow this formula, the formula says we take the natural abundance, that's those percentages, but we have to make them a decimal. And so for to figure out the average atomic mass of magnesium, I'm going to put magnesium here. We're going to take the 78.99 and make it a decimal. Well, I can do it in my head, but if you can't, take 78.99 and divide it by 100, because you had to multiply by 100 to get it to be a decimal. So it's 0.7899, and then it says natural abundance times the mass. Okay, the mass of magnesium 24 is 23.9850. Okay, we have to take that one, and then we're going to add it to the 10%, so as a decimal, 0.1000, and then times the mass of magnesium 25, which is 24.9858, plus the rest, which we said was 11.01%, so we'll make that a decimal, 0.1101, and times the magnesium 26. Magnesium 26 has this mass, 25.26. All right, now to put this in your calculator, be careful, okay? I'm going to do 0.7899 times 23.9850. I'm going to press enter. Then I'm going to press plus, but I'm going to use the quantity button, so the parentheses, plus parentheses, 0.1 times 24.9858. Close the parentheses. I'm going to press enter, plus then parentheses again, 0.1101 times 25 point, I can't read my writing, so I'll look back up at the problem, 9826. I'll close the parentheses, I'll press enter. And for problems like this, I'm going to say, let's do 2 decimal places for our answer, okay? We have 4 significant figures anyway, so this should take care of it. And so you should get the mass of magnesium as 24.31 grams. So do this in your calculator and make sure you can get that number. I'm going to grab a periodic table just to check and see how close I am. I'm going to look up magnesium, and my magnesium on the periodic table I'm looking at says 24.30. Well, I think 24.31 is within the tolerance limits for that, and so I'm going to go with that one. All right, you'll get practice with this on your average atomic mass worksheet, so we'll be able to do some more problems with that. Generally, the atomic mass is going to be closest to the mass number of the most abundant isotope. So if we take a look, if we have magnesium 24, I'll just do it like this, magnesium 25 and magnesium 26, without knowing the percentages, I could tell you that there is probably more magnesium 25 in this mixture than the other 2 isotopes, because my mass is closest to 24. And when you look at the actual percentages, you'll notice that 78.99% of it indeed is magnesium 24. And so most of it is magnesium 24. We will do more practice with this when you guys do your average atomic mass problem set. But if you have trouble, watch this video again and contact me by email or Teams or see me in class. So just make sure you have a calculator when you do this, and also make sure when you're calculating the average atomic mass that you use the parentheses feature in your calculator. So that, you guys will become pros with this in no time. So thanks for listening.